In the previous video, we discussed the behavior of the NPN transistor. And we said that as we increase the base voltage relative to the emitter, we forward bias this diode, and we inject a very small current into the base emitter, where this is the base terminal, this is the emitter terminal. And when that happens, a large current flow results from collector to emitter, where this is the collector. The PNP transistor behaves in a similar manner, except a lot of things are reversed. Let's draw the PNP symbol. This is the emitter. This is the collector. This is the base. Emitter. So what happens here is that the emitter base diode is forward biased. This diode is forward biased. So when that happens, we inject a small current in the base region, and that causes a current amplification from emitter to collector. So we inject a small current out of the base, and we get a large current flowing from emitter to collector. So let's examine the physical structure of the PNP transistor. So it has three different regions. We'll call this the emitter. Then it has a thin region that we call the base, and another region called the collector. Now this emitter region is a P-type material. This is a N-type material in the base, and again a P-type material in the collector, thus PNP. Now the emitter is very heavily doped with holes, and the base is very lightly doped. So when the emitter base junction becomes forward biased, we inject a large amount of holes into this base region. And most of these holes will flow across the base into the collector region. A small number will flow out the base terminal. So again, we have a very small base current, and we get a large current flowing from emitter to collector. We'll call this I sub C. And the physics of this is that the emitter is very heavily doped and the base is very lightly doped. And the base collector junction is usually reverse bias for the PNP and for the NPN. So I would like to draw the depletion region in the base collector. So there'll be depletion region that we discussed in the PN junction diode. And this is devoid of carriers in this depletion region. And there's a built-in electric field in this depletion region that is in this direction. And so when a hole comes into the base region and diffuses over to this collector, this base collector depletion region, it encounters this electric field that helps the hole sweep across the depletion region and into the collector. Let's draw the current voltage characteristics for this PNP transistor. So if I graph current versus voltage, where this is voltage emitter to collector, this is the current in the collector. If I run a particular base current into this PNP transistor, I would expect a characteristic that would look something like this. And eventually it breaks down. Now if I decrease the base current a little bit but keep it constant, I would expect the curve to move down and perhaps do something like that. So this is the breakdown region. And notice that, like the NPN transistor, there's a slight slope on this curve. And that's, again, is caused by this base collector depletion region. So as we move in this direction, we're increasing the reverse voltage on the base collector diode. And when that happens, this depletion region again extends further into the base region. And when that happens, the base region becomes thinner, and more carriers that are injected from the emitter into the base region then reach the collector region. So you get more current. The further this way you go, the more current you get. And that's the base width modulation. Again, as with the NPN transistor, there's a parameter called beta of the transistor. And that's equal to the collector current divided by the base current. And a typical beta could be 100. Or it can have a large variance. It could go down to 20, perhaps it could go to 150. It depends on the transistor structure and doping levels. Now let's do a simple circuit design using an NPN transistor and a PNP transistor. Recall from the previous NPN transistor video that we had a circuit like this. We have an NPN, we have an emitter resistor to ground, we have a plus 5 volt power supply. We had the base at a fixed voltage, 1.7 volts. And I believe we had a emitter resistor of 1 k ohm and a collector resistor of 2 k. We said that this performed amplification. As we increase the base voltage, we increase the emitter current, we increase the collector current. Because this collector resistance is twice the emitter resistance, we got a gain of 2. Now let's modify the circuit a little bit. Let's add a PNP transistor. Let's connect the base of the PNP to the collector of the NPN. Let's connect the emitter up to the 5 volt power supply. And let's connect the collector to a load resistor that connects to ground. And let's make the load resistor 1 k ohm. Okay, now one thing, let me just point out a few things about NPN and PNP transistor schematics. Usually when we draw a schematic, we'll draw the positive power supply at the top, and ground will usually be at the bottom. And the emitter of the NPN will usually be towards the ground terminal, and the collector will be usually towards the higher voltage part. And with a PNP transistor, the emitter usually connects to a positive supply, and the collector tends to usually connect to the more negative supply. That's basically because current will tend to flow in this branch and then in this branch from the positive supply to ground. So let's analyze what's happening in this circuit. Let me just erase this for a second here. Okay, let me change colors. Now we said that the base emitter drop is about 0.7 volts. So we have 1 volt at this resistor. So we have 1 milliamp in the 1K. And this 1 milliamp wants to flow into the collector because the beta is relatively high. And so most of the emitter current will end up in the collector. So we have, in the collector, we have 1 milliamp. And the base emitter drop for the PNP, like the NPN, a rule of thumb is about 0.7 volts. So this 0.7 volts limits the current in this 2K resistor, 0.7 volts across 2K. If I think that's about 0.35 milliamps. So that subtracts from the 1 milliamp, and the remainder of the current flows into the base terminal of the PNP transistor. So that is 0.65 milliamps. Now this 0.65 is going to be multiplied by beta. Let's say that beta is equal to 100. So in principle, we could get a lot of current flowing from the emitter to collector. If we multiply the 0.65 times 100, we could get 65 milliamps flowing. But notice that we have a 1K resistor in the collector region. So that limits the current. And what happens is that this tries to drive 65 milliamps, but this resistor limits the current. And what happens is that the collector voltage rises until this junction here. I'll draw the diode. There's a PN diode in the collector base junction. And this diode becomes forward biased, and the transistor conduction goes down. The voltage drop from emitter to collector could be on the order of, say, 0.2 volts. So that would give us 4.8 volts across 1K, which is 4.8 milliamps. So what has happened, that this resistor has limited the emitter collector current to 4.8 milliamps. So if we go back to our transistor curves, what has happened is we've limited this collector current, and we're operating in a region here where the voltage emitter to collector is quite small. It's somewhere around 200 millivolts. And this region is called the saturation region. So when this base collector diode becomes forward biased, this transistor is in the saturation